Okay, so let me remind you all, so we're talking about functions, right? And I'm gonna do a load of examples here, because even though functions are something from your past that, you know, you've been talking about functions forever with calculus, I think it's probably good to be careful about this. This is kind of our standard notation, right? Is a relation from a so subset of A cross B, and if A, B is in our relation, well, let's say it's F, because it's the name of our relation here. Then we write F of A. So a function is a relation, and this relation is not just any relation, it's got two special properties. Number one, the domain of F is all of A. So this is, you had like domain questions, like even in pre-calc, they give you the function of something like 1/x, and say, what's the domain? And you go, for A, everything except for 0, right? Because you can plug in everything except 0 to that. The domain function from A to B, domain is all of A. So in other words, you can plug in anything for A, or if you think of it in this notation here, there is a coordinate for every A and A that appears as somewhat coordinate. And two, not only is the domain all of A, but if X, Y, and X, C are in F, then Y is. The last time we talked about some beginning examples, and we talked about where the vertical line test comes from in the case that the function is from the reals to the reals. Let's look at some other examples here. Patient terminology. If F make B, it's a function, and A, B is in F, right? F of A, B, I've already said that, so let me give you some, we'll call these things here. We're going to refer to Y, or I'm sorry, B is the value. Or image of A under F. And A is the pre-image of B with respect to F. Okay, so if F of A equals B, then B is the image, and the pre-image of B is A. Here are a number of important examples of functions that will come up numerous times. This one is incredibly important right here, and it's used in a number of things. Called the identity function. On A. Or from A to itself, if you like. And it is defined by, what do you suppose the identity function does to an element in A? Takes it to itself. So this is the function from A to itself that just takes everything to itself. It's the identity function. Here's a generalization of this. Something a little bit more general. If A is contained in B, then that's supposed to be a Greek iota. Or include the function. Right. So for example, a concrete example of this is you might have, say, the rational numbers and the real numbers. And the inclusion map just takes every rational number to its corresponding rational number inside the reals, right? Here's another example. Y'all have all seen examples of inclusion. It's just named in as a subset. 3. Here's another one that you've seen examples of. Let's say A and B are non-empty. And let B be any element of B. Here's kind of a nifty function. Find F from A to B. This is the lazy person's function by F of A equals B for all A and A. So what have we done? We picked an element, some element B. There might be a whole bunch of them, but we just picked one. And we take everything in A and we cascade it on. Everything goes to the single element B. See how lazy I am? This is called the constant function. And you're familiar with this. For example, the function f of x equals, let me pick a real number 2. This graph is a horizontal line if A and B are the real numbers, for example. Here's another important one. This is called the characteristic function. Let x be set empty and a subset of x, then the characteristic function of A is a function that maps the entire set, X into the set 0, 1. And I mean the set consisting of the number 0 and the number 1, right? And here's the way this works. Chi A of X is equal to 1 if X is A, 0 if X is not an A. So basically what the characteristic function does is it goes through and its inputs come out of this master set X and it reads the point and it says, if the point is in A, it goes ding, 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 1. And if the point is not in A, it gives you a 0. Like this. You can define characteristic functions more generally, but this is kind of like engineers would dig on this, right? Because it's kind of a little binary thing, right? 0 means off, 1 means on, right? But yeah, you can generalize characteristic functions in a number of ways. So for example, so here's a sub-example of a characteristic function. You might have X be the real numbers and A be the interval from minus infinity to well, actually, A is the interval from 0 to infinity. What does the characteristic function do? Well, I can actually draw a picture of this. It reads all these over here. It says, hey, look, I'm not in A. Right? So I've got a big fat 0 here. And actually 0 itself is not in A. So it's a closed right here. Right? Then it reads over here. Everything to the right of y-axis is actually in A. So the characteristic function. So that's like engineer's love, right? Slide on, light off. That's what this does. But there are more sophisticated examples of characteristic functions. So for example, X be the real numbers, and A be the rational numbers. So characteristic function here is 1 if X is rational and 0 if X is irrational. So basically, what you've got is a spray of dots, right? So at 1, you have every rational point, like 0, 1, 1 goes to 1, 1/2 goes to 1, a third goes to 1, 5/4 goes to 1, etc., etc. And all the irrational numbers, it gives you a y coordinate on the x-axis 0, right? And I can't draw this one really, not with any justice, because this function is not continuous anywhere. Okay, how many of you have seen this function before? Seen it in calculus class maybe? Yeah, this is, if you've ever seen it in calculus class, it would be kind of like this pathological example. Oh, this function's not continuous anywhere. But you see probably the value of the characteristic function is it measures, yes, I'm in here, no, I'm not in here. And actually, the more general kinds of integration, you need characteristic functions. Here's an example that generalizes this. So what I want to do here let A be the set. Well, let's take it to be empty. And let P be a partition. Remember, this is just an index set that sort of counts this off. These are the puzzle pieces. What is true about all the puzzle pieces PI? If you put them all together, so let me remind you, PI intersect PJ. It's empty. If I is not equal to J. And the union. Well, what is the union?
A.
It should be all of A. That's right. Actually, I left out one of the properties of partition here when I write those two up. What did I leave out? It's a technical thing, but we want all of these sets to be non-empty, right? No empty puzzles. Right? Now, I'm gonna play fast and loose with you here. This is of course just a visual aid to help us out because I would expect this thing to have infinitely many puzzle pieces, but cities PIs. I want for every PI, I pick a point, which I will call BI, in, uh, uh, so we want to create a function from A to B. That's what we're heading for. And I'm going to use this partition to do this. Um, um, so we have A, you've got this A partition into the puzzle pieces. Now, what we have is we have another set here, B. B and B, whereas B is just some other set. So for each point B in this new set B, we select some partition that corresponds to. Let me get this here. I'll just see if they see about the same thing. We now define F from A B given by and only if A. So we're going to define a function from my original A into this new set B. we read A and we say, hey, where is A? Well, we partitioned the set here. So A is in one of these PIs, right? Has to be. And it can only be in one of them, right? Because this is a partition. So the partitions are all mutually disjoint. So if A lives in this PI, then we go to the corresponding PI. This generalizes. So you convince yourself this is a function. Because with the characteristic function, for example, with this one right here, we only partition the reals into two sets, the rationals and the irrationals, right? Well, we can partition a set into more than this, and this is how we might generalize that characteristic function to more than one element of the domain. You've seen examples like this. How many of you have seen the greatest integer function? Right, calculus. Does anybody remember what it looks like? Like a staircase. It's not continuous. This is you can get this from this kind of construction here. Here's another example. Oh, these. Example. How many of you remember doing sequences for Calc 2? Right. Well, you remember there are these things called sequences, right? What is a sequence first and foremost? Add a bunch of terms. That's a series, right? That's I mean, you're close, right? I know the terminology is not the greatest, right? I mean, how many of you have ever watched Law and Order or Game of Thrones, right? People say that's a series. That makes me very angry. It's not. Law and Order, Game of Thrones, that's a sequence, right? Especially the last season of Game of Thrones, it didn't really add up. So sequences are just a collection of numbers in a row. And you would often write this way. And you played with these in Calc 2, right? Here is a definition that you would see in a more mature book. Definition. A sequence is a function F from the natural numbers or real numbers. I explain where this comes from and how does that connect with what you know about sequences. How in the world is this function? Yes.
Because each natural number corresponds to n corresponds to a n.
There you
not
go.
necessarily a natural number.
Here's how the function works. He's exactly. Here, we're going from the natural numbers to the real numbers. So I'm going to list the natural numbers like this. And the AIs are just the outputs of the function. So these things are really the values of the function. So that's often you'll see this definition of sequence as a function from the natural numbers to the real numbers. Well, that string of numbers, what they mean by that is just the outputs of the function. All right, so this thing right here determines this function. Any questions? Here's this one's very good too. How many of you in here have passed modular arithmetic? I hear some of you talk about it quite a bit. example. And I'm gonna give you this example generally, and then I'll give you kind of, a good example of, concrete example. Okay, so let A be set. Again, this is on the side, okay, not empty. And tilde an equivalence. Define F of A. This is from set A to the set of its equivalence classes. F of A is the equivalence class of A under tilde. Here's sort of how this works. Here's the set A. One of the things we know about the equivalence classes is these are partition induced by whatever its equivalent expression is. And say that A is an element here. This goes to A and X. Let's say X is an element here. X goes to the equivalence class of X, and so forth and so on. So you go through A and you take any element, you find what the equivalence class it is, and that's where it goes. So here's a concrete example of this. Let's let A be the integers. And the equivalent class, the equivalence relation is given by if and only if the difference is this way. And let's see how this works. We want F. You go from C by taking, let's say, X, oops, regular X, goes both. So how does this work? Let's see. By the way, how many equivalence classes are there? The equivalence classes we got? Four. And how can you tell? Each one of them is represented by a possible remainder upon division by 4. I agree with. So for example, F 27 Because the equivalence class of 27 is the equivalence class of 3. Right? F of 81 is the equivalence class of 20. Everybody okay? So, example, let's let A equal. Now all have to be numbers. We will say that card 1 is equivalent to card 2 if and only if card 1 and card 2 have same seat. Now, we talked about this. This is an equivalence relation. F goes A to how many equivalence classes are there here? 4, 1 for each suit. I'll pick a representative. Ace hearts. Ace diamonds. Ace clubs. And ace of spades. Right. But they're aces or not aces, it doesn't matter. The equivalence class of the ace of hearts is the same thing. Equivalent class. Jack of hearts, 7 of hearts. Yes.
So how is, like A, or how is F from integers to like integers of the inverse classes? Like, how is that a function if like 41 and 81 have the same, like, go to the same?
That's fine, because everything has a unique output, so two different things can go to the same thing, that's no problem.
Oh.
You can't have a single thing try to go to different
Oh,
things.
okay.
Right. So F of the 4 diamonds is the equivalence class of the 4 diamonds, which is the equivalence class of the ace of diamonds. In fact, this example is similar to the last one. There'll be 13 things that go to the diamonds equivalence class and 13 go to the hearts and so forth. You might try to do the deck of cards from the suits point of view as well. That's also an equivalence relation. Right. Another example. Oh, it's not actually. Given a relation from A to B. So I'm just going to start to build this relation. But on the, like, I don't make a claim that this is a function yet. So R is a subset of A plus B. That's at this point not necessarily a function. Then we have two projection functions. This is just R itself is a set. Of projection functions. Hopefully you can see what this is all about. One. Have one from R into A. Now, I know it's hard to see for you all at this point, but again, the moral of the story is math. If it ain't easy, don't do it. All right? Input is something in this relation. Right? Subset of A plus B. So something in the domain of this looks like in order to pair A and B. What is the easiest way that you can cajole an element of A out of this? What's the most natural way to input this and give me an element of A?
Okay.
Just take A. And I'll write F1 for dramatic purposes. This is projection on the first quarter. All right, so your input AB, I can get the A just by taking it from it. I bet you can guess what the other projection or function will look like. F2 from RB. Suppose I actually will see what it's saying. B. Check that these are functions. It doesn't matter what the relation is, it just matters it's a subset of A cross B. Okay. Let me give you a theorem, which when I state it, I think you'll think is obvious, but we're gonna make sure that we tie any loose ends up. Two functions. G omega B are equal. If and only if yes.
At the B, so that would be for all A and A.
That's essentially it. Let me be super careful and say. Actually, let me just not even say that. Because where they're from, will be clear. For two functions to be the same, they've got to have the same input set. And what you all said, if for all X in a domain of F, we have that F X. Okay, so let's prove this. I think this is kind of obvious. This is what you would want two functions to be equal. They have the same domain, and whenever you plug something in, you get the same output. Yes.
You say that it's the two functions, also you consider that being additive function.
No, because my function might go from cars to pickup trucks. And if I subtract two pickup trucks, I don't know what I get. Right, that's the problem there. Let's suppose first that F and G are equal. So well, I'm assuming they're functions. So in particular, their relations. since F and E are relations, they determine same subset of A cross. See, once again, makes things a lot easier to just kind of assume that these things are relations, because their relations are more general and actually easier to deal with. So the domain of F, which by definition is A and A, such that A, B, and F is equal to the domain of G, which is set A and A, such that A, B, C, G. Since the ordered pairs A, B are the same for both of these, the domains coincide. Additionally, of X, if X is in domain F, which is the domain of G, then there exists C in B, well, let's call it Y in B, such that XY is in F and XZ is in B. So in other words, you get Y when you plug in X to F, you get Z when you plug in X to G, but as F is a function, and I could apply this to G as well, and XZ is also in F, this implies that Y equals C. So F of X. So I got both of these predictions. Now we suppose that the domains are the same, and we have that other condition. Now suppose domain F, domain P, and for all X in domain F, which is negative as well. So I want to show now that these two functions, or in fact, these two relations, that's easier to do, show that are the same. So I need to show that it's G. Now, of course, what is a function? Or generally, what is a relation? It is just some subset of A cross B. So what do I mean? Technically, and in my most primitive terms, what do I mean when I say two relations are the same? I mean, they are the same subset of A cross B. So to that end, let us suppose that AB is in F. So I'm writing this like a relation really, but of course what that means is F of A equals B. Well, this means that A is in the domain of F, which is the domain of G. because we're assuming that. And so. We're all, and so. By second condition. That is to say, since A is in the domain of F. F of A equals G of A. And of course, F of A is B. Hence. AB is in G. So I started with AB and F. And I got AB as G. So. Relation F, every AB in relation F is also in relation G. And also. I don't think I need to prove this part because all I do is, just swap out the, notation of F and G here. So, F is G, and we've got the other direction. Any questions on that? Okay. Now, we move up the ladder a little bit and start building some slightly more sophisticated functions. And I'm going to start with this. How many of you remember doing inverse functions when you're in, even pre-calc? Did you ever do the ones where they made you exchange y and x and then you solve for y? And then there was also problems with the trig functions, weren't there, right? Because most calculators have an inverse sine function on them, but they're not one-to-one. So the results for rigmarole went to. So we're going to start. And we're going to forget about this being a function. I'm going to write that this is a function, but we're going to forget about it. Suppose I walk up to you and give you a function here. This is a relation. More generally. So we have the inverse relation F inverse. What is that? Well, F inverse, just you'll repair yx where xy. Yeah. So f of x is equal to y, then f inverse y equals to x. But here I'm talking about a relation. By the way, does anybody remember? You can't have an inverse function for just any function. Anybody remember what the criteria was for a function that has these couple of nice properties to have an inverse function? Do I remember that?
That be one to one.
Right, and also technically onto as well. Now, as I pointed out, this is a relation. Not necessarily. Let me give you a concrete example of this. Where it's not necessarily. Make this one easy because you basically only one function you can do here. The domain has to consist of 1, 2, and it's got to go somewhere here. So this is really the only function, isn't it? Because the domain has to be all of this, and you're forced to send everything to B, right? So if I were to technically write this in relation terms, this is a function, right? Because this is a function because it's actually it has to be, right? No, nothing can go to more than one thing, in a certain sense of the relation. So the function is actually equal to this subset. Everybody agree with that? What is the inverse relation? Yes. Notice this is blatantly not a function because B is trying to go to two places. It's not a function. Notice in this example, our head was forced. Given my set here, there's really only one function. Right? And since there's only one function, there's only one inverse, which is not a function. Right? Yes,
You said onto and.
one to one. Which is,
What is?
it doesn't matter yet. I'm gonna get to that. I don't expect you to know that yet, but that's what, those are the concepts. One to one, okay, have you heard the horizontal line test? That's the old days for the one to one, and we'll talk about why that one works as well. Okay, but if you don't know that word, fret not, little soldier, we will get to it. Any questions? All right, well, we will see you folks on Wednesday.